Hi guys, it's Kate. This is a video of the walkthrough for the second practice exam for the Exponential Gateway. And believe it or not, I had to say that about 8 times before we got it right. Let's get started. The idea behind this video is that you can look at how these problems are solved, where you can develop intuition for what direction to move in, and also create some structures that will help you check your work and make sure that you're headed towards the right answer as opposed to just pulling it right out of thin air. Let's begin with the first question. Dubnium-261 is a highly radioactive substance, and every 27 seconds, half of it decays. So that 27 seconds is its half-life. If you have 4 pounds of dubnium, write a formula for the weight of the dubnium after t seconds. If you've watched the first video, you know that what I really prefer to do is create a table first. A nice table that just tells me at certain times how much I have left. So there are particular moments in time where I'm very clear about how much of this substance I have left, and that's what I'm going to highlight in this table. So on one side we'll have a timestamp, and on the other side we'll have the amount of dubnium that's left over. All right, the very first thing I know is how much I start off with. I know that at the very beginning, meaning times t equals 0, right? I have 4 pounds of dubnium. All right. Well, what's the next moment in time where I'm really clear about how much dubnium I have? That happens to be 27 seconds later. I know that half of the dubnium has decayed, and so I'll have half remaining, which means that if I were going to say that in a succinct way, that means when t equals 27, I've taken that 4 and multiplied it by 0.5. Okay, great. Now, what is the next time that it becomes pretty clear to me how much dubnium I have? Well, 27 seconds after that, I'll have half of that amount left over. And so I can write that by saying, hey, I also know that after 54 seconds, I'll take that 4 times 0.5, the amount I had after 27 seconds, and I'll be multiplying it by 0.5 again because the dubnium decays again, only 1/2 remains. And of course, a succinct way to write that would be 4 times 0.5 quantity squared. Now, I also know that 27 seconds after that, right, or when t equals 81, I know that I'll be multiplying this particular amount, the amount that I had after 54 seconds, and 50% of that will decay. So in order to calculate how much I left over, I take 4, I multiply it by 0.5, and then multiply it by 0.5, and then multiply that by 0.5. So in order to know how much is left over after 81 seconds, I'm going to calculate 4 times 0.5 cubed. Interesting. This should give me enough to work with. If you've watched the other video, you'll know exactly what I'm about to do next. If you haven't, this is a great starting point anyway. The general form of an exponential function is going to be some constant, which we'll call a, times another constant, which we'll call b, raised to some exponent. And this is just in general. I'm not even talking about in this specific example. This is in general. This is what exponential functions look like. And each of these pieces do a different thing. Note that when the exponent is equal to 0, meaning the starting off point for this function, the entire function, because when the exponent is equal to 0, b is raised to the 0th power and is equal to 1, the entire initial value depends on a. So usually this right here is responsible for the initial starting off value. The next piece that's really important is that b, that base of the exponent. That indicates the percent change that we're talking about. So whatever that multiplier is corresponds to the percent either increase or decrease that we want to have act on the amount of whatever we're looking at. And then last but not least, that exponent controls how often we multiply by that b. Let's apply this to our problem. For us, our initial value that we care about, that a, that should equal 4, right? That's the amount that we have starting off at the very beginning of all of this, before the dubnium starts decaying. We know that at t equals 0, we have 4 pounds of dubnium. So I would like my a to be 4. B corresponds to the percent growth or decay. For us, we're focused on when 1/2 of the dubnium decays, right? And the multiplier that we like to be multiplying by in order to calculate that is seen over here again and again in our table. That's that 0.5, that multiplier of 0.5. So for us, B here is going to be 0.5. That is what I like to multiply in order to subtract half of what I had before. Now the last piece is what's going on in the exponent. Now the exponent we said controls how often we multiply by B. Note that for us, how often we multiply by 0.5. We notice that over here there's going to be a pattern. When t equals 27, we are raising 0.5 to the first power. When t equals 54, we want to raise 0.5 to the second power. When t equals 81, we want to raise 0.5 to the third power. When t equals 0, we want to raise 0.5 to the, wait, it's not even there. Oh, but it is. We're raising 0.5 to the 0th power over here. All right, let's think about this. How can we connect some expression for t up in the exponent so that when you plug in 27, you get 1? That's a big hint. When you plug in 54, you get 2. When you plug in 81, you get 3. And in fact, what that means for our exponent is that we want to take t and divide by 27. Think about that. Now you can, in case you're still skeptical as to whether that is our answer, right? You can take a second and start to plug in all these values in our table to make sure it's correct. If we plug in 0 for t, note that this zeroes out the whole exponent, this turns into 1, this whole thing evaluates to 4. This statement is correct. If we plug in 27 for t, this exponent becomes 1. We're now taking 4 and multiplying it by 0.5. This statement is correct. When we plug in 54, we now have 2 up in the exponent. We have 4 times 0.5 squared. This statement is correct. Same thing for 81. This becomes 3, and this statement is correct. And so this is going to be our formula for the weight of the dubnium after t seconds. Let's take a look at the second problem and approach it in much the same way. This time we're depositing $4,700 into a bank account. And the bank account earns 0.5% interest every month. Write a formula for the amount in your account after Y years. And already we're seeing that there are bold-faced words here, and it's calling out that even though interest is accrued monthly, we need to be writing our ultimate formula in terms of years. So when we start this table, right, we want our Y to be in years, but we want the interest to sort of take into account the fact that interest is in terms of a monthly interest. Let's see how that works out. My first question for you is right when we're starting off, how much money do we have in our bank account? Well, right when we're starting off, Y is equal to 0, right? That's our timestamp. And we have $4,700. All right, when is the next time that we know how much money is in our account? Well, we know after a month that we've earned 0.5% interest. And so what does that mean? Well, after a month, how much has passed in terms of years? A 1/12 of a year has passed. So Y is equal to 1/12 at this point in time. And how much money is in the account? Well, 4,700 times 1 plus 0.005, right? That is the multiplier that you need to use to calculate 0.5% interest. When's the next time you know the bank account balance? After the next month, right? After the next month, you're going to be multiplying by 1.005 again. Now, when is that? Well, that's going to be after another month has elapsed, or when Y is equal to 2/12. And just like we said, we're going to take that initial balance and we're going to multiply it by 1.005 squared. Because what we're doing is we're taking the amount we had in our bank account after the first month here and multiplying it by 1.005 again to have it accrue another 0.5% interest. And this is going to continue, right? When Y is equal to 3/12, then we're going to be calculating 4,700 times 1.005 cubed. And this pattern will continue. In fact, I'd like to ask you, what would happen after a year? How many times would you have computed the accrual of interest? Well, you would have computed 4,700, right, times 1.005 times 1.005 times 1.005 times 1.005. You'd be multiplying by 1.005 12 times because every month the interest would accrue. So it's good to have this value in your table as well for a sanity check, that after a year you'd have 4,700 times 1.005 to the 12th power, because you're multiplying by that at the end of every single month, and a year is composed of 12 months. So let's get started. We now want to use the same approach that we did up here, but in this particular context. Remember that A quantity is responsible for our initial value. For us, our initial value is 4,700. That's the amount that the account starts off with. Then we have to figure out this multiplier that corresponds to either the percent growth or decay. For us, this is growth, right? Interest increases the amount of money in your bank account. For us, the requisite multiplier that would simulate a growth of 0.5% is 1.005. So we want to multiply by 1.005. And now the question becomes, what do we do with the exponent? We want the exponent to be some function of y. Note that when y equals 1/12, we want the exponent to be 1. When y equals 2/12, we want the exponent to be 2. 3/12, we want the exponent to be 3. And maybe even most tellingly, you may have already deduced what the exponent needs to be. But when y equals 1, we need the exponent to be 12. And so we see that in each of these cases, the exponent is 12 times y. And so we're going to write that in. This is all raised to the 12y power. All right, you can always go back, and this is our final answer here, but you can go back and check to make sure that that's the case. If you plug in 0, do you get 4,700? You sure do. If you plug in 1/12, do you get 4,700 times 1.005? You do. Plugging in 2/12, it's correctly raising 1.005 to the second power, 3/12 to the third, 4/12 to the fourth, so on and so forth. And most tellingly, when you plug in 1 for y, meaning a year has elapsed, you are multiplying by that factor 1.005 12 times, one time for every single month. All right, let's move to some conceptual questions about how exponential functions operate. For these next two questions, I'm going to do them very quickly because there is a much longer worked out answer with the video for the first practice exam for the Gateway. So if you have further questions, please let me know, but I'm going to try to keep it pretty brief here because the walkthrough exists. It's the exact same identical number 3. The first question asks us about a radioactive isotope. It loses 20% of its mass every day, meaning that at the end of the day, you have 80% of what you started with. Which of the following is true? Over 4 days, does it lose 80%? Does it lose more than 80%? Does it lose less than 80%? The correct answer is that it loses less than 80% of its mass. Because while it's true that you lost 20% of its mass every day, that 20% corresponds to a particular raw amount. When you then remove 20% of that amount, you're taking 20% away of a smaller number. So the raw amount decreases. Meaning if you take a quick look at what happens when you're going from 100 to start off, decreasing by 20% gives you 80. Decreasing by another 20% is going to give you 64. Note that the raw amount change, yeah, sure, you lost 20 at first, but then you lost 16. And that amount is going to get smaller and smaller, even though it maintains the rate of decrease at a constant 20%. Because you're taking 20% of a smaller and smaller number every day, this is not going to equal 80% of 100. This is going to be 20% of 100 plus 20% of 80 plus 20% of 64 plus 20% of about 51, and it will keep going. It's not going to be a total of 80% of 100 being what's lost. So number 3 is going to be that the isotope loses less than 80% of its mass. Now the same thing goes in the opposite direction. If you have growth and you have 20% growth or something like that, right? It will move from 100 to 120, but then it's not going to move from 120 to 140. It's going to move from 120 to 144. So if you're going to go in the opposite direction, this goes to 120, this goes to 144. And so you notice that the raw amount is not going to be 20, 20, 20, 20, 20. It's actually going to get bigger and bigger and bigger. And so the effect of even just 20% growth over 2 days is not going to be 40%. It's actually going to be 44%. So when you're looking here at a credit card that has a 24% annual interest rate, what does that mean about your balance? Well, if you had exactly 2% growth every month, doing that 12 times would actually end up giving you more than 24% over the course of a year. So if you want to hit exactly 24% over the course of a year, that means each individual month has to be growing by less than 2% monthly. Again, if you're confused about these two ideas, in the Practice Exam 1 walkthrough, they are gone through much more slowly with more time attributed to them. Let's take a look at the next batch of questions. This tells you if you write the exponential function y equals 4 to the t plus 4 over 2 in the form j times k to the t, what is j and what is k? Basically, we really want to isolate t up in the exponent. There are many ways to solve this, but the first thing that bothers me is that there are these parentheses. I have t plus 4 quantity divided by 2. So I'm going to get rid of the parentheses first. So I have y equals 4, and if I have t plus 4 divided by 2, I'm going to distribute that 1/2 multiplication across the addition in t plus 4. So I have t over 2 plus 2. And so all of a sudden I see that I have addition up here in the exponent. And one thing that reminds me of is this property of exponents that says if you have the same base, such as x to the a, and you multiply it by x to the b, the result is going to be x to the a plus b. That's the net result of the exponent. Why is that? Well, x to the a is just x factors of a. So you have a terms here. And then you multiply that by x times x times x times x b times. So that's b terms in here, which means that in total you have x times 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 x. All of this, we have a plus b terms. And because multiplication of real numbers is associative, meaning we can do it sort of in whatever grouping we want, this is the equivalent of taking x and raising it to the a plus b power. There are a plus b factors of x there. So we're going to use that here. We see that this particular comment here, 4 to the t over 2 plus 2, this seems like the result of reversing this property. That I'm starting here and I'd like to break it into two different things. So what that leaves me with is that y is equal to 4 to the t over 2 times 4 squared. That is reversing the property that we just discussed. All right, that's pretty exciting. So I'm going to put this 4 squared right in front. So I have 16 times 4 to the t over 2 power. And now I have a product of two things up in that exponent. I have t times 1/2 up here. And I'm reminded of another property of exponents. That property of exponents says that if I have x to the a and I raise that to the bth power, that's the equivalent of taking x and raising it to the a times b power. It's kind of difficult to say that out loud. Why is that true? Let's think about what happens when you have x squared and you cube that, right? That's the equivalent of taking x squared and multiplying it by x squared and multiplying it by x squared. Cool? Everyone agree with that? All right, and that means that I have, that is x times x times x times x times x times x. Or look at this. Every time you look at x squared, that's 2 factors of x. And then when we cube it, that's 3 sets of 2 factors, right? So ultimately you end up with 6 factors of x, or their product. It's also important to know that this is also equivalent to x cubed squared, because then you'd have 2 sets of 3 factors of x multiplied all together. All right, for us in particular though, this means that we're going to reverse this again, right? This is sort of saying, hey, I could go from this expression of x squared, all of that cubed, and re-express it as a product of x being raised to the product of 2 and 3, being 6. Here we already have the product, and we'd like to separate that product into the individual factors. And in particular, we want to take this and we want to separate it into individual factors so that one of those factors is t, and the other factor is whatever the other term in the product is. For us, that means that y is equal to 16 times 4 to the 1/2, all of that raised to the, whoopsie, tth power. There we go. That does the job. And from there, we're able to write down exactly what our final answer should be, because we just need to figure out what 4 to the 1/2 is, which is just the square root of 4. So I have y equals 16 times 2 to the tth power, and so that means that j equals 16 and k equals 2, right? Let's see how that walked through from the beginning. Here, the first thing I did was distribute that factor of 1/2 in order to get rid of these parentheses. So I was left with a power of t over 2 plus 2. I noticed that if I reversed this effect, I could separate. I really want to isolate the t. I want to get it away from all these other terms. So the first thing I did was separate it from the plus 2 in here by reversing what we usually do to simplify things. So I separated that into 4 to the t over 2th power times 4 squared. This became my coefficient down here. I still needed to separate this out, and I exploited this property of exponents. In fact, moving from product into, this is the result of the product, into the two different terms that you would multiply to get there. And so this left me with 2 to the t. And so that was how we got to this place right here. Let's move right along. This is a typical graphing problem, and one of the things that I find students really struggle with is they are tempted to just try to graph it all in one swoop. And I just say, I mean, I don't even do that. That seems totally daunting and way too intimidating for me. So I want to start with sort of the simplest exponent, that it's exponential function that's at the heart of this function, 2 minus 2 times 3 to the x minus 1th power. And then through a series of graph transformations, I'm going to take that exponential function and build it up into the function I'm required to graph. For me, I'm going to start with I'm going to ignore this 2 minus blah, blah, blah. I'm going to ignore the 2 times blah, blah, blah. I'm going to even ignore the x minus 1 and just start with a basic 3 to the x. What does that look like? Well, it's just a gradual exponential function over here. Note that it has a nice y-intercept at 0, 1. That's where I'm starting. Now, let's see if we can make this a little more complex to start matching this particular function. The first thing I want to do is consider what happens if I'm looking at 3 to the x minus 1th power. Now, what's interesting about this is that the output that we used to get, for instance, when x was equal to 0, is now the output that we'd get with our new function when x is equal to 1. The output that we used to get when x was 1 with our old function is the output we now get if x equals 2. And it's because of that that we associate this manipulation of the input as a shift rightward by 1, right? The function value that we used to get at a particular value for x is now what we get for one value greater in the input. So let's try and do that. I don't know if this shift is going to be so apparent. I now have a particular point here that has been shifted 1 to the right, right? So that's now 1, 1. If you still want to figure out what the intercept is, that's still going to be 0, and now it's going to be 1/3, because if I plug in 0 in for x, I have 3 to the negative 1, which is 1/3. All right, what if we multiply by 2? I'm slowly trying to build towards this. I'm now going to multiply by 2, okay? Well, multiplying by 2 means that we're increasing the function value by 2, or a vertical stretch. Something like that. What happens to each of those points that we had labeled? Well, the input stays the same, but the output gets multiplied by 2. Again, the input stays the same. The output gets multiplied by 2. So this right here is 2 times 3 to the x minus 1. Now, of course, I'm not just multiplying by positive 2. I happen to be multiplying by negative 2. Right? That's what I'm looking at up here. What happens when I multiply this whole thing by negative 1 so that I have negative 2 times 3 to the x minus 1th power. Well, changing the sign of the function value is what it's going to do, which means it's going to flip it over the x-axis. So here I now have something that looks like that. Sorry, I'm now writing on this text here. So this changes the sign of the output. So this now becomes 0, negative 2/3. This point would become 1, negative 2. I flipped it right over. It didn't change the magnitude, it just changed the sign. This is negative 2 times 3 to the x minus 1. And so our last step is to finally add on this plus 2 to the whole thing. And this is where we're finally going to be able to graph our function. Now, adding 2 is just a vertical shift. Note that I'm going to write in all the different things that we did to lead up to this point. And so our final result is that we're going to shift it upwards by 2. Now, up until now, we've always seen that there's a horizontal asymptote at y equals 0 that has not changed through any of this. Now that horizontal asymptote is going to happen at y equals 2 because of that upward shift by 2. So I'm going to sort of draw that in and say that this is y equals 2. That's my asymptote. Note that I didn't want to try and do a dotted line. It felt like something I wouldn't really be able to do, but if I were drawing this in green as my solution, I would do something like that to make sure it looked like an asymptote and wasn't anything confusing. It's not part of the function. All right, so then the next piece is that I want to take this old drawing of the function right here and I want to shift it up by 2. Now, this is definitely going to move this into positive territory. This is now 1, negative 2 is now going to be right on the x-axis, and I've really lucked out by tracking that point. That was sort of unintentional. It became an x-intercept, but I will take it. Thank you very much. Let's see, if I added on 2 to negative 2/3, that's negative 2/3 plus 6/3, so 4/3. A little bit more than 1 is going to be my y-intercept there. So I'm going to give this a whirl. I'm going to try to move through. I know the points that I've been tracking in red are now going to be here, 0, 4/3, and 1, 0, because we've taken that function value that was down here, right here, and added 2 to it. So that's now a 0. I've sort of lucked out here because this has become a intercept, and I've found 2 intercepts just by tracking points along the way. One was intentional. I kept track of what that y-intercept was the entire time, but it was nice that that point that had started out as the y-intercept, which shifted to the right, actually ended up becoming the x-intercept. That was somewhat lucky, but you know, I'll take it. So we'll draw this in. I feel nervous about it. So we turn through there, turn through there. Oh, that was terrible, but it worked out. Now it says I also need to label one point that is not an intercept. I would like the computation to be as nice as possible for that. So I'm going to pick -1, and I'll say -1, comma. And then over here I'm going to plug in 2 minus 2 times 3, and then I have -1 minus 1. -1 minus 1 is, of course, -2. So I have 2 minus 2 times 3 to the -2, which is equal to 2 minus 2 over 3 squared, or 2 minus 2/9. And of course, 2 is 18/9 minus 2/9. This did not become super cute. So I have 16/9 as the other component over here. So I have 16/9. So -1, 16/9 is the other point that I elected to label. And that's that. So I would really encourage you to work through these steps in this particular way, not trying to go straight to the graph itself. Let's continue. We're actually going to take a lot of how we understood this to work in number 5 and apply it to number 6. So what's interesting about number 5 is that it wasn't until we added that constant at the very end that we turned it into 2 minus 2 times 3 to the x minus 1, or you can think about it as adding 2, that we were able to shift the asymptote. So when we're faced with this type of problem, where you have a times b to the x plus c, and we want to try and write it down given this particular picture, I notice that the asymptote is at -5, and I know the only way for that to happen, the only way to move the horizontal asymptote away from y equals 0 is to do a vertical shift. So right away, just by looking at this, I know that because this has shifted downwards by 5, this tells me that c is equal to -5. That's the only way for that to happen. All right, so I can update my idea here, and I can say, okay, just by looking at the picture, I know that y is equal to a times b to the x minus 5. Not sure what else happens, but that's it. I'm going to label a couple of these points for my own sanity. I know that this is 0, -1. I know this is 1, -3. I know this is 2, -4. Yeah? And here's what's going to happen. I know that -5, that vertical shift is going to happen. What I find really useful is if I undo the vertical shift, if I shift it back up so that the horizontal asymptote is at y equals 0, it's much easier, computationally speaking, to then figure out what a and b are. And I can sort of ignore c, but I need to be very careful with this. When I shift it back up, just for the purposes of finding out what a and b are, right? I can have this particular function, and I want to figure out what all of these points are on here. So if I'm shifting up by 5, I didn't really draw this to scale, but bear with me. Note that that means the function values have all increased by 5. So this particular function value that used to be -1, it increases by 5. That means that this function value here is 0, +4. Then we go to, I'm adding 5 now to this function value right here. Adding 5 to -3 is 2. So I know that this particular point should be 1, 2. And then if I had a final point there, I'm adding 5 onto -4, which is the function value down here. So it's +1. And what I've done is just make my life a little bit computationally easier. This is the function before the shift. So this is the function before we subtracted 5. This is y equals a times b to the x. Right? This is, and this one here is y times y equals a times b to the x minus 5. So this is it before the shift, this is it after the shift. And this one is much easier to figure out what a and b are equal to without having to deal with constantly sort of subtracting 5 or adding 5 when you're doing the algebra. So for us, let's plug in 0 for x. That's going to cancel out b to the x. That's going to make it switch to 1 and isolate a by itself. That's going to tell us exactly what a is equal to. So using this point and plugging this into the function will tell us what a needs to be in order for that point to be passed through by the exponential function. So that means y equals 4, and we have a times b raised to the 0, right? I'm just plugging that point into this function format for the exponential function. That means that 4 is equal to a. Whew, we can now update our function. So we have 4 times b to the x minus 5. And then we can use one of the other points, knowing that a is equal to 4. We know then when x is equal to 1, y is equal to 2. So that means we have 2 equals 4 times b to the first power. Whew, my goodness. So if we take 2 and we divide it by 4, we get 1/2. And we know that that's b. Easy as pie, right? So we've solved for a, we've solved for b. It's much easier to do when you've unshifted. If you don't unshift, you can still solve the problem, but you'll find yourself continuously like adding 5 and all this algebra before you actually get to start figuring things out. So here we've found out that b is 5, which means our final answer is y equals 4 times 1/2 to the x minus 5, and that's our final result. And you can double check your answer by plugging in 0, -1, 1, -3, 2, -4, and you'll find that this function does satisfy each of those relationships. With the simplify as much as possible problems, you just absolutely have to know your exponential properties with great confidence. Before I jump right into them, here's what they are. We've talked about a couple of these already. One is that if you have the same base but two different exponents, you have x to the a times x to the b, then your result is going to be x to the a plus bth power. We've explained why that is. Let's take a moment and explain why x to the a over x to the b is equal to x to the a minus bth power. Well, that would mean that x to the a would be x times x times x times x times x, all of that. There would be a terms up here. And down here you have x times x times x times x. There would be b terms down here. And you're like, wow, I have so many common factors, right? And in fact, they would start to cancel out. That would be so exciting. And what you end up with is x raised to, well, the number of terms that survive is going to be the difference between the number of terms you had in the numerator and the number of terms you had in the denominator. Note that if a is greater, there will be terms that survive in the numerator, which is why a minus b will be positive. If b is greater, there will be terms that survive in the denominator, which is why a minus b will be negative. So what's left over is x to the a minus b. All right, so that's important to know. I'm going to erase that because we just don't have like a ton of room. All right, and the last piece that we want to definitely note is that if you have x to the a, all of that raised to the bth power, that is equal to x to the ab, which would also be equal to x to the b8th power, which would also be equal to x to the bth power, all of that raised to the a. And we discussed that in the previous problem as well. If you have any questions about those, you need to ask your TF or your CA. These are things that you shouldn't just be memorizing. You should really deeply believe. And I would encourage you to plug in actual values for A and B, like 2 and 3 and 4, and like write out all of the different products so that you aren't just taking these by face value, really believe in them. Let's get started to see what's happening. The first one is that we want to simplify this as much as possible. We have 2a quantity to the x plus a to the 2x minus the square root of a to the 4x plus a to the x all over a to the x. And it seems pretty likely that since we're dividing by a to the x, we really do want to rephrase or restate each of the terms in the numerator in terms of a to the x. All right, let's see how to do that. Well, the first thing here we have a lot of parentheses involved. And so when you raise a product, a quantity of a product, like if you have xy and you raise that to the bth power, right? What that's saying is you have xy times xy times xy times xy. That's b times. There are b terms that do that. And so really what you end up with is, because multiplication is commutative and associative, meaning you can do it in whatever order you want and group it however you like, you would end up with b terms of x and b terms of y. And so what that means is that this x times y quantity to the b is going to be x to the b times y to the b. For us, this means that 2 and a, right, those are the two terms in the product, this can be written as 2 to the x times a to the x. I'm going to totally leave a to the 2x alone. That looks pretty simplified to me. I now subtract, I want to restate the square root of a as a power of a, so that's a to the 1/2 to the 4x plus a to the x, all of that over a to the x. Now the only one that needs some slight massaging is this. And this is one of these examples where you have something where everything inside the parentheses is raised to a particular power. In this particular case, it's 1/2. And then all of that is raised to the 4x power. And we want to take the product of 1/2 and 4x as the total exponent acting on a. So I'm going to rewrite everything else. 2 to the x, a to the x, plus a to the 2x, minus a, this is to the 2x because I'm taking 1/2 and multiplying it by 4x, plus a to the x, all of that over a to the x. And right away I feel pretty lucky because I see a to the 2x minus a to the 2x, and so I know that these two pieces cancel. I'm now left with 2x, a to the x, I should say 2 to the x, a to the x, plus a to the x all over a to the x. And I see a common factor of a to the x everywhere, so I'm able to cancel this out. My final answer is 2 to the x. Remember that there is still a common factor of 1 right there. And that is my final answer. Completely simplified. 2 to the x plus 1. Let's continue. The second is very similar. We basically want to figure out what common factors we have to work with and then see what happens from there. In the numerator, let's see, I have 4 to the x, and I also have x to the 0th power, which is going to be 1. So I note that I could rewrite that as 4 to the x by itself. Note that that equals 1. And then I subtract off x squared raised to the nth power. Now, similar to before, if I have everything in the parentheses being raised to a power and then raise all of that to the nth power, the ultimate effect is raising x to the product of those two exponents, or 2n. Now, what's down here in the denominator is pretty tricky. You may remember that if you have something like a plus b times a minus b, if you went to expand that, you'd ultimately end up with a squared minus b squared. And it's the fact that a squared minus b squared, or a difference of squares, factors into two individual terms, a plus b and a minus b, that you might notice that, oh, this is what looks like a factored version of the difference of squares. You could also distribute each of these terms across the addition and realize the same thing, but it's nice because you're like, okay, if you see that it's a difference of squares, you're like, I know that what's in the denominator is x to the n quantity squared minus 2 to the x quantity squared. And so that can be something that I'll rewrite as well. So here in the numerator, I still have 4 to the x minus x to the 2nth power. In the denominator, I now have x to the 2nth power minus 2 to the 2x power. And you might be stuck. You might be saying to yourself, I have no idea how this works. This is very confusing. But 4 to the x, it actually can be re-expressed with a base of 2, because what power of 2 is 4? Well, 4 is 2 squared. So we have 2 squared raised to the x power minus x raised to the 2nth power over x to the 2nth power minus 2 to the 2x. It turns out that we actually have in our numerator, we're now seeing that everything inside that parentheses is raised to the 2nd power, and then all of that's raised to the x power. So that is 2 to the 2x minus x to the 2nth power over x to the 2nth power minus 2 to the 2x power. So what's interesting is that we now have identical terms in the numerator and denominator. We're taking the difference in both situations, but the order is swapped in the numerator versus the denominator. What does that mean? Well, they're not exactly the same, but it does mean that if I factored out a -1 out of the numerator, right, I would have x to the 2n minus 2 to the 2n over x to the 2n minus 2 to the 2, oh, I should have called that x up there, I apologize, to the 2x. And lo and behold, we now have a common factor of x to the 2n minus 2 to the 2x power. That divides out. All that's left is that -1, and so we're done. That is what's left over. That is fully simplified. This whole thing simplifies to -1. 2 more problems. Here we go. This first one you can absolutely, when you're simplifying, you can absolutely say, you know what I want to do? I want to expand everything and then see what cancels. Alternatively, maybe your eye was caught by the fact that there are a lot of base 2s and there are a lot of base 4s exponents, and you'd really like to just have everything in one base. So what's interesting is similar to the previous problem. Remember that 4 is 2 squared. So if you go about doing that as your first step, you'll have, there's nothing to re-express in the first piece. So we have 2 to the 2x power plus 2 to the -2x power, all of that quantity squared, minus, and then I have 2 squared to the x power plus 2 squared to the -x power, all quantity squared all over 2 to the x plus 4 to the x. And I'll even, let's go back there and say 2 quantity squared to the x power. Nice. Okay. So what's interesting about this is that this piece right here, right, 2 squared to the x power, well, that is just going to be 2 to the 2x. This right here, right, is 2 to the negative 2x. We're pros at this point. And so if we go ahead and rewrite this, we end up with 2 to the 2x plus 2 to the negative 2x quantity squared minus 2 to the 2x plus 2 to the negative 2x quantity squared all over 2 to the x plus 2 to the 2x. We realize that we have two identical terms in the numerator. This term is exactly the same as this term. So we have something subtracted by itself, right? We are subtracting off basically x minus x is what's sort of up there in the numerator. It's like the two identical terms. The difference between identical terms is 0. And so this entire numerator, right, this whole thing equals 0, which means that the entire thing, the whole expression, 0. Done. And that's it. Our very last one, let's check it out. Here we have lots of a's, lots of x's. A good idea when you're simplifying as much as possible is just to get rid of like the square roots, and you want a nice clean base raised to a nice clear exponent. So let's take a look. We also have some pieces that are a little confusing because we have negative exponents in different places. So some people like to right away start to put something like x to the minus a. We want to put it down in the denominator and bring this up to the numerator. So we're certainly happy to do that. I'll do a to the x times a to the 2x. I'm going to put all the a's sort of in one order and the x's on the right-hand side. So I have times, now this particular term here, right, that means everything underneath the radical there, that's the cube root. So that's raising everything under the radical to the 1/3 power. So I have a to the x to the 1/3 power, and all of that is being raised to the 9th. And then I also have this guy who's coming up to the numerator because it had a negative exponent where it was. Cool. All of that over, I'm doing everything involving a first. Remember that this is under a square root, so it's really everything in there is being raised to the 1/2 power. So I end up with a to the 12x plus 6 to the 1/2 power times, I still have an x to the a here, x to the a, but then I have one up here, right, that's joining it, times x to the a. And you might already notice that this right here is x to the 2a. And so these two and this will cancel, right? They will divide out. Now what's left over? I agree that these two combine into a to the 3x, right? Same base, different exponents. The rest of this needs a little bit more of an algebraic massage. So I have a to the 3x, cool. This part right here, note that this is a to the x to the 1/3 to the 9th. So this is gonna be a product of many things. First, we want to multiply 1/3 and 9 together. That's gonna be 3. And then you're raising a to the x to the 3rd, so that ends up being a to the 3x as well. So this becomes times a to the 3x. And then all over, we want to take 12x plus 6, the whole thing, and multiply it by 1/2 in that particular case. So I have a to the 6x plus 3. Whew. I have same base with exponents in the top, so I want to add those exponents together to get the total exponent. So I have a to the 6x over a to the 6x plus 3. And so that really means that I have 6x factors of a in the numerator, so it's like a times a times a times a. And there are 6x terms here. That's a big number. And then down here I have a times a times a times a. And I have 6x plus 3. So I have 3 more than 6x in the denominator. And so when you go about canceling, you're like, yay! And in fact, everything in the numerator will cancel. and then all but 3 terms in the denominator will cancel because I have 3 more than 6x in the denominator. So what is going to come out here at the end of everything is going to be 1, because that's all that's left in the numerator. And then those 3 terms of a survive in the denominator, and that's it. So I have 1 over a cubed is my final answer there. Of course, if you have any questions at all, please don't hesitate to ask. You also could have arrived at that final answer, by the way, by taking a to the 6x minus 6x plus 3 and found that to be a to the 6x minus 3, seeing that those two cancel and you're left with a to the negative 3. All right, as always, email if you have any questions. Good luck studying for your exponential gateway.